Welcome. Today we look at functions which appear in probability theory or statistics. The first class of functions are called probability density functions, or abbreviated PDFs. So that's the first part. And let me just give you the definition. So a function, a piecewise continuous function, is called a PDF. Probability density function, if two conditions are satisfied. So first of all, we want f of x to be bigger or equal to 0. And then we want to have an integral to be 1. The integral from minus infinity to infinity, f of x dx is equal to 1. So this is a total probability. We will just see examples. And the first example which I want to tell you about is the exponential distribution. And so what we take is f of x is equal to e to the minus x if x is bigger or equal to 0 and 0 else. We just draw that function here. So that function is 0 when x is negative. And then it starts at 1 and goes to infinity, goes to 0 exponentially fast. So this is our function f of x. And it's clear that this function is piecewise continuous. It has a jump here, but we just are interested only in x positive or 0. And it's clear that it's positive or 0, so the function. And we have to also check this identity minus infinity to infinity f of x dx. So when we do that, we have to split it up going from minus infinity to 0, which gives us 0, that's 0, so it's only counting from 0 to infinity e to the minus x dx. And we know the antiderivative of e to the minus x. This is minus e to the minus x. And we evaluated it from 0 to infinity, 0 to t, the t goes to infinity, and so this is equal to minus e to the minus infinity minus it plus 1, which is equal to 1. So this is indeed a probability density function. You see also this is a case where improper integrals really naturally occur in mathematics. A very important example of a probability density function is the normal distribution. Let me write down the function. So it's f of x is equal to 1 over the square root of 2 pi. And then we have e to the minus x square half. Let me draw the graph. So this is going to 0 when x goes to infinity or minus infinity. And so it's 1 over 2 pi here, and it goes to, so it's something like that. It's also called the bell curve. The Gaussian distribution. It had been Gauss around 1800 who realized that this function really captures errors one sees, for example, in astronomy. And already Kepler or Tycho Brahe have made observations and analyzed errors. But Gauss came up with this nice model, and it is now called the Gaussian distribution. It's not so obvious that, so first of all, the function is non-negative, that's clear, but it's not so obvious that this function is really a probability density function. So what we have is that this area here below the curve is equal to 1 is not obvious. So it follows from this identity here, integral from minus infinity to infinity, e to the minus x squared half dx is equal to the square root of 2 pi. I'll show you just in a second a little video where this problem appears.
I see you're looking at a little problem.
In this movie Gifted, Mary is given a problem. The problem which we have just looked at, compute the total probability of a normal distribution.
Well, for starters, you forgot the negative sign on the exponent. It went downhill from there. Problem was unsolvable.
The problem actually uses some multivariable calculus to be solved. We have not done that in single variable, but here she uses a double integral. If a probability density function f is given, we can define the cumulative distribution function. fx is a CDF. Then the antiderivative, integral from minus infinity, we go all the way from minus infinity to x, f of t dt. The CDF, the cumulative distribution function. Let's call it with a capital F, like it's an antiderivative. So what happens is f prime is equal to f of x. What is nice about this function, it is monotone, it increases in general, and it's continuous, it's always continuous. While f is only piecewise continuous, this is always continuous. And let me just give you a couple of examples. So if f of x is this exponential function which we have seen, right, the exponential function which is 0 here, so this is f of x is equal to e to the minus x, then the cumulative distribution function is just the antiderivative of that. So when you integrate from minus infinity to x, what we get is the integral from minus infinity to 0 plus the integral from 0 to x is really what counts. And then so we have e to the minus t dt, which is equal to 1 minus e to the minus x. So in this case, this cumulative distribution function is it's 0 here, and then it decreases strongly, but then it goes to asymptotically to 1. So this has a horizontal asymptote at 1. Actually, all these CDFs have an asymptote 1. So that's the first example. Let me give you another example. So if you have the uniform distribution on an interval, already seen that. So if f of x is equal to 1, if x is between 0 and 1 and 0 else, that's this uniform distribution. So it's 0 here, and then 1 here, and then 0 here. So in this case, this is the f. Then the cumulative distribution function, it's 0. And then it starts, it grows linearly here from 0 to 1, and then it's like that. So that's at 1. So that's the That's the cumulative distribution function in this case. In the case of the exponential distribution, in the case of the normal distribution, so if f of x is e to the minus x squared over square root of 2 pi, in this case there is no antiderivative known here which we can write down in terms of one knows if you cannot write it down in terms of sine x, the exponential or cosine or log, any of the known functions, but f of x is then just called the error function. This is the error function. Very important function. You find tables in every statistics manual, and what happens is this function comes from 0, goes up here, it starts to grow more, but then it also is asymptotically, it's asymptotic to 1. So that's the function f of x. And so this is the cumulative distribution function. You are computing it for a couple of more examples in the... Okay, let's look at another notion of probability. So we have the following interpretation. If we integrate from a to b, f of x dx. So f is a PDF, right? And then we have the interpretation. The interpretation that this is the probability that the data are in the interval a, b. For example, the exponential distribution is a waiting time. So, example, so f of x is equal to e to the minus x. This is a waiting time. Could be the waiting time for your next email you get, the next text message or next telephone you are getting. So this is a waiting time, and so the waiting time is always positive. You are not going backwards in time, so that's why we have here only x positive. So that was the picture, right? So that was the waiting time here. So what happens is the probability is larger initially, and then it goes to 0. So waiting for a bus or whatever you are waiting for an event to happen, that is usually exponentially distributed. And if you have an interval a, b, for example, if we have 1 and 2, so what we compute here with this is, so we also write here p a, b. So that's a probability, and this is an area under the curve. So this is the area under the curve over that interval here. So we can say what is the, if these are hours, we can say what is the probability that we get an email between the next hour and the now hour after. So let's just see that in this case. We integrate from 1 to 2, and then we e to the minus x dx. So this is e to the minus x minus 1 to 2. So this is e to the minus 1 minus e to the minus 2. So that's 1 over e minus 1 over e squared. 1/3 minus 1/9. It's a little bit less than 1, probably 1/3. So we can compute this. Sometimes we make here a square bracket too. As f of b minus f of a. So in this case we have already got the f of x, right? That was 1 minus e to the minus 6. So it's 1 minus e to the minus b was 2 minus 1 minus e to the minus 1, and that's the same thing. That's e to the minus 1 minus e to the minus 2. So if a probability density function is given, a distribution is given, then we have a improper integral minus infinity to infinity x times f of x dx is called the mean. The mean of this distribution. Let me just get a few examples. So you will do a lot of more examples in the homework, but let's just take the example when we have the exponential distribution. So this is e to the x, e to the minus x. So in this case, that was the distribution here. In this case, so we have to integrate, this is 0 here, we have to integrate from minus infinity to 0 is 0, so we only have from 0 to infinity x times e to the minus x dx. So now we don't know what the antiderivative is here, and we will learn some technique on the after next lecture how to do that. It's called integration by parts. For now I have just to tell you what the antiderivative is. So it's e to the minus x times minus 1 minus x. And we evaluate it from 0 to infinity. When I'm taking infinity here, then this is 0. This limit when t goes to infinity here, that dominates. I mean that kills this part, and it goes to 0. So at 0 we get 1 here, and we get minus 1, so we get equal to 1. So in this case the mean is 1. So that's the mean in this case. In example B, where we had just the uniform distribution from 0 to 1, so the function was 0 everywhere except on the interval from 0 to 1. In this case, if I'm computing the mean, so we integrate from 0 to 1 only because this integral and this integral is 0, and then we have x times the function is f is equal to 1 here, right? So times 1 dx, which is x squared half, evaluated from 0 to 1, that's equal to 1/2. So in this case, the mean is equal to, it's here, the mean, this is the average. Or in this case, the mean was 1. In this case, the mean was 1/2. In the case of, you compute it in other cases like the Cauchy distribution or the arcsine distribution or the standard, the normal distribution in the homework. So that's it for today. I'll see you tomorrow in class.